So hello everyone, welcome to the talk. So today I'm going to talk about our work, a framework for software diversification with IC Heterogeneity. My name is Xiaoguang Wang, and this is a joint work with my colleagues, Simon Yang, Rob Leary from Virginia Tech, Pierre Olivier from the University of Manchester, Sang-Ho Kim from Ajo University, Binoy Ravajan from Virginia Tech. So let's talk about the background and motivation first. There are a lot of software defenses and program diversification mechanisms. Some of them are static. For example, the stack canary, the control flow integrity, they are all instrumented in the program binary. However, most of them, this approach may suffer from the static analysis. For example, given a long period of time, attackers can always figure out the ways to bypass the protection. On the other hand, there are some other dynamic software defenses mechanisms. For example, the runtime code randomization, the dynamic system or network configuration, or dynamic program diversification. Most of those approaches are mostly targeting a single hardware platform. So it may have this issue that those approach may have this deterministic hardware platform matrix. For example, the ISA characteristic or cache timing. So recently, there's a trend that the processing units are becoming more and more heterogeneous. This is because the end of the Moore's law has pushed the vendors to rethink the hardware design. For example, there are a lot of the AI workload running on the data center. Those workloads are running on top of the CPU, GPU, and even TPU combined environment. And recently, Intel also announced their new processor, which has the integrity of the FPGA. And on in the data center, a lot of the x86 servers are equipped with smart NICs. So those smart NICs are often running on ARM cores. Can we just leverage those heterogeneous hardware for dynamic software defense? The big picture is, can we just run those server applications on top of the heterogeneous ISA environment and randomly select changing the execution path or running diversified applications? So the question is, there's a question. So how can those multi-ISA systems help in securing the software? There's some prior efforts. Those kind of work has proposed to use the multi-ISA chip to prevent the rope attack, the return-oriented programming. For example, in Hipster, this is a work in S+ 17, and it just used Gym5 to simulate those multi-ISA chip. And it also used some dynamic binary translator to translate the program execution state. However, their approach is based on this hypothetical multi-ISA chip. It is unclear what are the security benefits and the performance overhead on real hardware. Can we just leverage those existing heterogeneous machines to build such ISA diversified secure applications? So what are the pros and cons of such system on real hardware? To answer this question, we built Heterostack, which is a framework to enable diversifying the applications with multi-ISA on commodity scale. So this is the outline of this talk. Next, we are going to talk about the system design, and we'll talk about two security applications on top of the Heterostack. The first is multi-ISA moving target defense, and the second one is called the multi-ISA multivariant execution. After that, we'll talk about the implementation details and evaluation result. So this is an overview of the heteroSAC. The heteroSAC, we connect the ARM server and x86 server with an InfiniBand. And we also implement the fast in-kernel messaging channel. So with the channel, each node can exchange the data with the counterpart node very fast. And on top of it, we also have this distributed OS kernels. It provides and process shared virtual address space. For example, global data and heap data are virtually shared on those two nodes. And also, we have the OS-related resource synchronization. For example, the application can access the descriptors and socket in a virtually shared way. And it also handles the cross-ISA code execution. For example, it transforms the program state from one ISA to the other. And it also deals with those architecture-dependent data structures. Based on that, we built two applications. Those applications diversify the program, leveraging the multi-ISA hardware feature. So the first application is called the Moving Target Defense, or MTD. So in this application, we randomly execute code on ISA different nodes. And the second application is called MVX, or multivariant execution. The basic idea of MVX is to run two instances of the same program, but they will be running on the ISA different nodes. And at runtime, we check whether the instance behavior will mismatch. If there's a abnormal behavior, like a crash, or if there's an inconsistent behavior, we will deduce there's an potential undergoing attack. So let's talk about the first security application. It's a multi-ISA MTD. What is MTD? So the moving target defense is a mechanism, or it's a concept to break the static nature of the target system. For example, it still export the same interface to the outside world, but inside the system, it can be changed. It can be changed, can be very dynamic. For example, existing works uses dynamic configuration to make the attackers harder to attack the target. So with heteroSAC, we try to dynamically change the execution environment, which is the ISA, for the running process. So we randomly choose the code path at runtime. So heteroSAC has the ISA differences for the application execution. Those differences can be the ABIs, application binary interface, or register sets, or even program state. So this is an illustration of how this process goes. heteroSAC provides this per-process shared memory for global data synchronization. And at runtime, whenever we have this ISA switch request, it will call a trampoline code. Those trampoline code, in our case, are at each function boundary. So basically, at each function call, like entering the function and exit from the function. The trampoline code will rewrite the stack. And for example, it will synchronize the stack live values, and it will synchronize the architecture-dependent current data structures. So this code is from our existing work in ASP.17, and after the code is executing for a while, on the other side, whenever there's a ISA request, it will transform the control flow back to the original node. So in our case, the ARM machine. So by doing that, we provide a random execution path with two different instruction set architecture. So the second application is called multi-IC MVX. So the basic idea of MVX is to run multiple functionally equivalent program, but with different memory layout. And we feed them with the same user input. So by observing there is an abnormal behavior like a crash, so the MVX monitor could deduce there is a potential attack. So existing ways to generate the variant include like non-overlapping memory or the different stack orders. So in our approach, we try to leverage the ISA, the diversified instruction set architecture to generate the variants. So basically, we just compile the same source code into different binaries, and we just run those binaries on different machines. So at runtime, our MVX monitor will check the system call sequences and the return values. If there's a memory corruption, we will report those kind of attack. And similarly, with the existing MVX monitor, we also simulate the system calls. This is because some of the system calls can be only executed on one variant. For example, if there's a socket connection and if there's an incoming package, only one variant could handle this event. And in that case, we just simulate the system call effect to the second variants. And with Heterogeneity, we still do the lockstep checks on the system call sequences and return values. And so there's some kind of some details in this brought by the multi-ISA environment. For example, the system call names will be different. For example, on ARM, it will call this open at, where however on x86, it will call open. And also those system call numbers are different. The same system call will have the different number on different architecture. To solve that, we introduce a translation table which can match those different system call names and binaries. So with our multi-IC MVX, the variants are generated based on the architecture, and we also leverage the existing address space layout randomization to make it the memory non-overlapping. Okay, so next we move to the system implementation. The distributed OS kernels have this kind of in-kernel message channels. This in-kernel messaging channel avoids the context switch between the user space and the kernel space. So it can be very fast for the communication between the nodes. And it hooks on the VMA and PT operations, which implement the virtually shared memory. And for system calls, the distributed kernel will simulate some system calls, and it also forward some system calls and signals on demand. For the cross-ISA code execution, we just leverage the Popcorn compiler to generate the multi-ISA binary. And we also do the rewrite. We also do the stack transformation during the control flow transformation. And beside the system call sequence translation table, we also have a table to translate the descriptor access. For example, if we are accessing some descriptors on the follower node, we will use this descriptor table to forward this request to the original node. There's some other details like pointer updates and architecture specific data structure handling, which we will talk about this part in the next slide. So we in heterostack, we also introduce a new system calls to indicate the heterostack process. Okay, so more details are in the paper, but in here we just talk a little bit about some pointer update and architecture specific data structure handling work. So we will use a case, a system call case like fdat. So basically, if the follower node try to issue the fdat system call, we can see they have a parameter called struct stat. So in this case, the kernel need to copy this kind of the file status to the user space. However, in this case, only the master side maintains all those file information. So in this case, with heterostack, we just the kernel just redirects the system call with the system call server, and it is like RPC style system call handling, and it forwards this request to the original node, and on the original node, because these data structures are different with each other, each architecture. So we will do this kind of format conversion. And on the master side, when after it prepared this data structure, it just called their own copy to user to the user space, and the user space memory are synchronized with each other, and so so there's a circle just synchronizes this data structure to the user space in this way. So this is a prototype of heterostack. We built the heterostack on top of Cavium Thunder X CPU and Intel Xeon E5 CPU, and they are connected with Connect X for InfiniBand. The modified kernel is based on the Popcorn Linux 4.4, and it transformed the state. And for the second application, for the MTD application, the compiler and linker extension is required. So we ran several benchmarks, include MPB, MBench, and some other real-world applications like Nginx, Redis, Lighty, and gzip. So first, we do the security analysis. So we first analyze what is the benefit, what's the benefit of those architecture impact. For example, some of our observations include those general register set. Also on ARM, it has more general registers, and in result, the stack layout are different. And there's some other things like function call parameter pathing on x86 machine. It can be there are 6 registers can be used for pathing the function call, but however on ARM they will have more registers to pass the parameters. And we also observe this kind of frame pointer and link registers location are different. So some details are in the paper, so curious readers can read the paper for more details. We also investigate the microarchitecture behaviors. So on different architecture, the ways to measure the timing and the precision are different. And also they use a different way to flush the cache line. So it's very hard to conduct those kind of attack that targeting both architecture with the same source code. And we also scan the code and data layout to find all those pointers at runtime. So we use the Lighty web server, and we found 7,000 something pointer instances on the x86 side, and we found 10,000 pointers on the ARM instances. So when we align the base address we can only find like 3 overlapping pointer addresses. But if we enable this ASLR, we cannot find any overlapping pointers, which means giving us the same input, it will be very hard to find those locations on different architecture. We also investigate this kind of this Nginx CVE, this attack to the MTD application, and it can defeat this attack. Next, we'll talk about the performance evaluation. We use a micro benchmark to measure the system-wide metrics. For example, we measure the raw network ping pong, which only have 17 milliseconds, and which is much faster than the pin latency. This is because we have a faster in-network communication channel. And with a remote system call, we can see the remote get PID is just the number from the get PID plus the raw network ping pong. And for the ISA switch cost, it's still reasonable. Next, we'll talk about the performance evaluation of real applications. So first, we measure the MTD performance, which randomly switches the code path. And for this Nbench benchmark, we have the different probability of ISA switch and we can see it has 50% slowdown compared to the vanilla application execution. We also measure some server application like Redis server. So Redis server is a memory and IO intensive application. We measured on 3 scenarios. The first, we use the local host, the local internet, and second, we use artificial latency of 10 milliseconds to simulate the edge computing scenario. And third, we inject this 40 millisecond network latency to simulate the cloud computing scenario. So we can see with the local network, the performance is quite slow. This is because the ISA switch is kind of costly. And but for the edge computing and cloud computing scenario, the performance is acceptable. They only have like at most 20% performance slowdown. And next, we measure the MVX performance. So we ran 2 instances of the application on top of a different node. And we have our heterosec kernel-based MVX at the yellow bar, and we also use a p-trace-based MVX monitor that is shown at this light blue bar. We compare the result for the Nbench benchmark. Most of the CPU intensive benchmarks, we don't have any slowdowns, but for those IO and also memory intensive benchmarks, we can see with Heterogeneity, we have 50% slowdowns, while with the p-trace-based MVX monitor, we'll have more than 10x performance overhead. And this performance is even better than the state-of-the-art MVX monitor called Daemon. Okay, so next is summary. So we present Heterogeneity, a framework to diversify program using ISA heterogeneity. And we built 2 applications on top of it. And though that's pretty much of the talk. And please feel free to leave us some questions. And the source code is available as part of the Popcorn Linux project. You can get the source code by accessing this website. So that's all the presentation. Thank you.